Hello students, welcome. Previously, lesson 2, form 4, topic 4, we were dealing with oxidation numbers. So today, lesson 3, we are going to go to electrochemical cells. Electrochemical cells are also known as voltaic or galvanic cells. So what are electrochemical cells? So electrochemical cells are devices that use a chemical reaction to create or to generate electricity. And we are told the type of chemical reaction that they use to create electricity is specifically an oxidation reduction reaction. In other words, it's specifically a redox reaction. So we are told a battery is an example of an electrochemical cell. So next we are told an electrochemical cell is formed by combining two half cells. The electrodes of the two half cells are connected by metallic wires, while the solutions of the half cells are connected through a silt bridge. So if we check, this is the diagram for an electrochemical cell. So we are having the two electrodes, it's connected through a wire. So this is the metallic wire that we have. And we are told the two solutions are connected through a silt bridge, and that's the silt bridge. So we are saying a half cell is an arrangement in which a metal rod or electrode is dipped in a solution of this ion. So in our case, this is a half cell, this side. This is a half cell because a half cell is an arrangement in which a metal rod, like in our case metal M or metal M rod or M electrode, is dipped in a solution of its ion. That is solution containing M ions. Okay, this is the other again half cell. It's composed of metal rod dipped into solution of its own ions. So next we are told electrode potential is the quantity used to measure concentration of electrons on the rod or the electrode. When two half cells are connected, the more reactive metal gets oxidized. Remember we said oxidation, it is loss of electron. And so in bracket we have loses electrons, while the least reactive metal gets reduced. So that means reduction, we said, that is gain of electrons. So in other words, gains electrons. Okay, so here we have two electrodes, anode and also cathode. So anode is the electrode in which oxidation takes place, while cathode is the electrode in which reduction takes place. So in our case, this side is the anode electrode. This is where we are having the anode electrode. And here it's where we are going to have the cathode electrode. So when you are told what is anode, anode is the electrode in which oxidation takes place. So this side, metal M, loses electron. So those electrons lost goes through the wires and they are gained in this other half cell. So that's the cathode, because cathode, it is where reduction takes place, and reduction, that's gain of electrons. So this is the diagram for the general electrochemical cell. So here it is the left hand side of the electrochemical cell, and this is the right hand side of the electrochemical cell. So remember, the more reactive metal is placed on the left hand side, that's the anode, because the more reactive metal has high tendency of losing electron when compared to the least reactive metal. So the least reactive metal is placed on the cathode or the right hand side of the electrochemical cell. You have to know that. So remember, when we are dealing with the electrochemical cell, we had something called silt bridge, and we said silt bridge, it is what is connecting the two solutions. This solution of M ions and also N ions are connected by a silt bridge, as you can see. So what is a silt bridge? So a silt bridge is a filter paper soaked in a saturated solution of potassium nitrate or sodium nitrate. We are saying sodium nitrate and potassium nitrate are preferably used as silt bridges, and the reason for this is that because they can't lead to the formation of precipitates. Remember, we have the rule all nitrates are soluble. So that means they will not lead to the formation of precipitates. So what is the function of the silt bridge in an electrochemical cell? One, we are told it completes the circuit by making contact between the two electrolytes or contact between the two solutions. As you can see, this is the silt bridge. It is connecting the two solutions. That means solution containing M, metal M, and also solutions containing metal N. Okay. The second function or role of the silt bridge is it maintains a balance of charges in electrolyte by providing ions to replace those ions that are used up or those that are formed. So next we are having notes. We are told electrons follow along the wire from the anode to the cathode electrodes. So here we are having, this is the anode electrode, and we are having the metallic wire here. So that means flow of electrons will be from the anode towards the cathode. So the arrow will be from the anode going towards the cathode. That will be how electrons follow through the wire. So next we are told the difference between the electrode potential of the two electrodes is called electromotive force. It is written EMF, which is measured in volts using a voltmeter. So in our electrochemical cell, we are having here this V, that's for voltmeter. That's the instrument for measuring that electromotive force, EMF. It's measured in volts using voltmeter. Next, we want to go to cell diagram, which is also known as cell representation or cell notation. So we are told cell notation is the shorthand for writing down the cell formed by connecting two half cells. So in our case, we are having two half cells. This one, the first half cell, and this other one, that's another half cell. So we have general cell notation here or cell diagram. We're having M solid. This is phase boundary, that vertical line. We're having solution of M ions. We're having double vertical line again, which represents the silt bridge. And here we're having solution of zinc ions. And we're having phase boundary, that means a single line. Then we're having that side of metal Z. So here, when you're writing cell notation, the more reactive metal is placed on the left hand side. So M is the rod or the solid of that more reactive metal, and Mn plus solution will be the ions of the more reactive metal. For example, if we are dealing with the cell notation for the side of maybe we are dealing with the zinc. So we are dealing with zinc half cell, and also we are having another half cell of copper. We are having copper half cell. So we have to ask ourselves, first of all, between zinc and copper, which one is more reactive? Zinc is more reactive. So that means the zinc will be the first one to be written, and the state will be solid. Then we are having phase boundary, that vertical line. Then we are going to write the solution of zinc. Zinc loses 2 electrons and forms zinc 2 ions, which are solution form. Then next we are going to have 2 vertical lines to represent the silt bridge. So next we are going to write now the ion of the least reactive metal. So we are having copper half cell, that means it will be copper 2 ions, which are in solution form. Then we are going to have phase boundary. Then we are going to write the solid or the metal of the least reactive metal. This is how we are going to write cell notation or that cell representation. So we are told the single vertical line, that vertical line here represents the phase boundary in which potential difference develops, while the double vertical lines represents the silt bridge, and that is the silt bridge here. So next we are going to go to examples. The first example, we are told draw an electrochemical cell connecting a copper half cell to a zinc half cell. So we are supposed to draw electrochemical cell. Remember, we have said electrochemical cells is formed by connecting 2 half cells. One half cell here is copper half cell, the other half cell is zinc half cell. So let's just try to draw the general structure of the the electrochemical cell. So how are we going to draw? We are going to have here a beaker, and this beaker we are going to put the electrode. Then this will be another beaker, and we are going to have the electrode or the rod there. These two electrodes are connected through wire. So, and here we have an instrument called voltmeter. Then we are supposed to have the cell bridge. This will be our cell bridge, and this is the solution. So, solution. So this is our wire. This is the cathode electrode, and this is the anode electrode. So we are having zinc half cell and copper half cell. So between zinc and copper, which one is more reactive? Zinc is more reactive. So here the anode will be made up of zinc electrode. So here we are going to have zinc rod or zinc electrode. On this cathode side, it will be made up of that copper rod or copper electrode, copper rod. That will be. So here we are going to have solutions containing cobalt-2 ions. We can take cobalt-2 nitrate solutions. And here we are supposed to have solutions containing zinc-2 ions, so we can have zinc nitrate solutions. So this is the cell bridge, and we can have potassium nitrate to be as our cell bridge. So I've drawn the electrochemical cell connecting a copper half cell to zinc half cell. Okay. Romeo 1, we are told write the ionic equation where oxidation takes place. So oxidation takes place at the anode, because anode is the electrode where oxidation occurs. So what is oxidation? Loss of electron. So here we are going to have zinc, which is solid, losing electron. When it loses electron, we are going to get zinc 2 ions, and those electrons lost are written on the product side or the right hand side of the half ionic equation. So next we are going to go to Romeo 2. Reduction takes place. Reduction takes place at the cathode, and there we have cobalt-2 ions, first of all, which are in solution form. Then the electron lost from the anode are gained at the cathode. So plus 2 electrons. Here we are going to form neutral copper metal. So we are going to have that as our half ionic equation where reduction takes place. So next, we are having on the diagram indicate the direction of electron flow. So we said electrons follow from the anode towards the cathode. So that will be flow of electron. That is it. So we move to Romeo 3. Romeo 3, we are told write the overall ionic equation for the cell. So for us to write the overall ionic equation for the cell, we are supposed to add these two half ionic equations. How are we going to do? We are going to have zinc solid, then arrow, we are going to have zinc 2 ions in solution form, plus the 2 electron lost. In the other half ionic equation, we are having cobalt-2 ions, aqueous, plus 2 electron gained from the anode, giving us neutral copper metal. So we are going to sum up this two half ionic equations. So here we are having zinc solid, so we are going to write zinc solid on the reactant side, plus. So these ones are product side. I'm going to take cobalt-2 ions again. I'm going to put it on the reactant side because it is on the reactant side. So these 2 electrons here will go with these 2 electrons there. So if you see something on the reactant side, if you see it or if they appear on the product side, you are supposed to cancel them out. So arrow. So the product that I have there is zinc 2 ions, which are solution form, plus I have again here copper solid. So this is how you are supposed to write the overall ionic equation for the cell. Next, I'm told state the observations made. So here we have several several observations. So the first observation, we can check first of all the electrochemical cell. It is like that. So this zinc rod or zinc electrode loses electron. That's what we have said. When it loses electron, it wears out and goes into solution as zinc 2 ions. So that means the observation that we are going to see on this rod is that zinc rod dissolves or decreases in mass. That will be the first observation. So we can say zinc rod dissolves, or in other words, zinc rod decreases in mass. That's the first observation. So second observation, we are going to see again, we said those electrons that are lost will go through the wire or follow through the wire, and they are going to react or Cob2 ions, which are in solution form. So when Cob2 ions gain 2 electrons, we are going to get copper metal. So that means they are going to be deposited on the copper rod. So that means the size of this will increase, or this copper rod increases in mass. That will be the second observation that we are going to see there. So we are going to say copper rod or copper electrode increases in mass. Okay, the third observation. The third observation, we can check here. This half cell, which is on the right hand side, was blue in color due to the high concentration of Cob2 ions. But Cob2 ions that were having the blue color gain 2 electron loss from the anode to form neutral copper metal, which is red brown in color. So that means the blue color now fades or disappears. That will be the observation that we are going to see. So we are going to say blue color of Cob2 nitrate fades. That's what we can say. Fades, or in other words, disappears. Then the last observation that we can see is that there is a deflection on the ammeter. There is a deflection on the ammeter. That will be the other observation that we are going to have. Lastly, we are told write the cell representation for the cell formed above. So here we are having 2 half cells connecting a copper half cell to zinc half cell. So between copper and zinc, we say zinc is more reactive. So we are going to have zinc, which is in solid form. Then we are going to have a vertical line to represent phase boundary. Then we are going to have solution of zinc 2 ions, which are aqueous. Then we are going to have double vertical line to represent the salt bridge. Then we are going to have Cob2 ions, which are in solution form. Then phase boundary. Then we are going to have copper solid. So this will be the cell notation or cell representation. So but B of that question 1, we are supposed to draw an electrochemical cell connecting a copper half cell to silver half cell. So I have to draw first of all again the general electrochemical cell. So here I'm going to have my beaker, the first half cell. Then I'm going to have the other beaker here. Then I'm going to have my rod, the electrode. Then this is for the electrode for the second half cell. Then I'm going to connect them using salt bridge. This is my salt bridge. So I'm going to use wire to connect the 2 half cells, and in between I can put voltmeter. So I'm going to put the solutions here. So we're having solutions. So now this is the wire. So This is the salt bridge. So let us see the ones that we are going to put on this side and the one we are going to put on this other side. So between silver and copper, which is more reactive? Copper is more reactive. So we are going to put copper on the left hand side, copper rod or copper electrode. Then we are going to put silver rod or silver electrode on this other side. Remember, this is the anode and this is the cathode. So we have copper rod, which is anode. Then we are having here the copper rod, we are going to put it anode. Anode is the one that's negative. Then here we are going to put the cathode as our silver rod. Remember, cathode is the one that's positive. In our previous one, we are supposed to put the anode to be negative, then the cathode to be positive. Already we have written positive there. Okay, so we can put our salt bridge to be sodium nitrate solution. And here we are having solutions containing cobalt-2 ions. And here we can have solutions containing silver ions. Okay, the first, from here A, we are told write the oxidation half cell. Oxidation occurs at the anode. So anode, we have copper rod. We have copper rod, as you can see. So copper is solid. So it loses 2 electrons to become cobalt-2 ions and goes into solution. Then 2 electrons lost are written on the right hand side of the equation. So the reduction half cell, we have silver rod there. Silver is written Ag. So solution, it will gain the 2 electrons lost from the anode to form silver solid or silver metal. But we have to balance to put 2 here. So the 2 electrons is lost, 2 electrons is gained. Then we're having 2 silver, we have to put 2 here, say 2 silver there. Then indicate the direction of flow of electron on the diagram. To do that, we are going to have an arrow there. Then we go next, we are told, write the overall equation for the cell shown above. So for us to do that, it's not must for us to take these two and we put them together, we sum up as we have done in the first part A. But what we can do is we can write copper solid there, copper solid, ballast. We're having a 2 of silver solution, aqueous. Then these 2 electrons will go together. They are going to be just, they will go out. We will cancel them. Then we're going to have cobalt-2 ions solution, ballast, 2 of silver solid. That's how we are going to write our overall cell equation. Lastly, from year 4, we are told write the cell notation for the cell shown above. So here we are having copper to be the more reactive metal. So we are going to have copper solid. The phase boundary, we are going to write cobalt-2 ions, which are in solution form. The salt bridge, we are going to write silver ions, which are in solution form. Phase boundary, then we are going to have 2 of silver solid. So this will be our cell notation. That's the end of our video.